Hi, this video is the second episode of the course, and in this video, we will be talking about the base speed and a slot pole combination and the calculation of line to line terminal voltage considering a three-phase inverter. As I said in the previous video, we will drive the motor by a battery pack that the voltage of the battery pack is 72 volts. So what we need in analytic design is line to line, the RMS value of line to line voltage. So we need to calculate that value. So I will explain how we can calculate the line-to-line RMS voltage considering this DC value. We need to consider a three-phase inverter. Okay, let's start. As you know, we have two operating regions for a synchronous motor, a constant torque region and constant power region. As you can see here in this figure, the constant torque region is when the terminal voltage is lower than its rated value. In this region, we can feed the stator winding by stator phases by their rated values. So we can generate the maximum torque, maximum output torque, but at the base speed, the terminal voltage equals its rated value. So beyond this speed, we have to reduce the terminal current. So this is the constant power region. The constant power region, also known as flux weakening region, because in this region we need to reduce the motor deflux because of reducing of induced voltage in phases. Because we need to reduce the induced voltage because of injection of current. Let me show you this curve. This is supply voltage and stator resistance, leakage inductance, and phase EMF. Okay. In IPM motor, if you consider a magnet flux lambda m, the EMF, the induced voltage in every phase, is proportional to lambda m and the motor speed. So if you consider a constant value for lambda m, when motor speed increase, the induced voltage increase. So when this value equals terminal voltage, we cannot inject current in a stator winding in phases. So we can't generate electrical torque. So we need to reduce the component of air gap flux by injection of a negative the current. Okay, I will explain this in the next videos when we calculate the static torque and when we calculate the torque speed curve. Okay, just this was a short review. So let's talk about the motor rating. This sheet here, as you can see in these specifications, in these specs, the motor output power is 4 kilowatts. This is the rated value. The design should be able to deliver this power at this speed in its steady state operation. What is a steady state operation? A steady state operation is a condition that motor can operate without any thermal issues. So, uh, if you consider 4 kilowatt as rated power and 1800 as motor speed, the rated torque will be equal. This is omega m mechanical speed, that is equal rated speed times pi divided by 13. Mechanical speed is equal rpm times pi divided by 30. Okay, let me cut these cells. This is this calculation. And I write here rated torque. This is just a calculator. I calculated rated torque there, so let me delete this one and paste it here. Yes, this is output power times y 1000, because this is the unit of rated power is kilowatt, and we need to convert it to watts. Okay, so the rated torque is equal 21.22 Newton meters. For determination of main dimensions of motor, as you can see here in this Excel sheet, for determination of main dimensions, we need to consider output power, speed, line-to-line terminal voltage. Okay, so how we can determine the rated, the operating point, the steady state operating point. This is torque speed plan. Mechanical torque, electrical torque versus mechanical speed. And this is the rated output power and the rated speed. So let me plot, for example, there. I write omega m rated value, that is equal 1800, and the rated torque there, that is equal 21.22. The unit here is Newton meter, and the unit there is RPM. So, if you consider 10% our design there and 10% our design there, so we have this curve. We have this curve, and so 10% I write this is the rated torque. I write TE our design is equal this times let me define a variable there first. I write torque our design percent. I write 10. This is I define a design variable there that is easier to use. So the value of electrical torque in our design case is equal to rated torque times this plus 1. Okay, and again this is Newton meter and this is Newton meter. So if we select this point as a steady state operating point, and if we consider 10% our design in electrical torque and 10% our design in speed, so how we should fill these cells, the numbers here. So calculate the power in this point, okay, and in this point I write the point number 1, the point number 2, and the point number 3. So the output power is equal T times omega. When the output power is maximum, when we have high value for torque and high value for speed. So we know that P2 is higher than P1 because the speed is the same, but the torque here is higher, and P2 is higher than P3. So we should consider the worst case, right? So we design the motor to operate at this point in its steady state operation. So I define another variable there and I write speed our design. Again, let me specify the format of this cell in percentage. So I defined these design variables so you can change these margins based on your considerations. Okay, and I write omega m our design is equal this speed times 1 plus this number. The unit is radian per second, and let me write speed our design, okay, that is equal this times 1 plus our design in speed RPM. Okay. The output power in our design case is the output power in our design case is equal T times omega m in our design case. This is in watts, so I should divide this by 1000. So this is kilowatts. You can increase the precision here. Yes. Okay. So these are rated values. The motor should be able to deliver 4 kilowatt at this speed continuously. And we considered 10% our design, both in torque and in speed. And we calculated this output power. So I said these cells equal to these numbers 4.84, 4.84, and 1980 as rated speed. So the motor dimensions will be calculated considering this operating point. This is equation for consideration of base speed, and I explained this equation here, and I implemented the equation there. So let's summarize this section. We considered a point on torque speed plan as a steady state operating point, and we set the ratings here in main dimension sheet equal to these calculated values. The next topic is selection of the number of poles. Here we have this relationship between motor speed, the motor speed, and frequency of supply, and the number of poles. So already we know the value of RPM. We have set the value of RPM equal to this number 1980, and by considering a value for the number of poles, we can calculate the frequency of supply. So for example, if we select 4 as the number of poles for the motor, so the supply frequency will be equal 67 Hertz. And if we select 6 as the number of poles, the frequency of supply will be equal 100. And if the number of poles equals 8, so the frequency of supply is 133. So what is the best number for the number of poles? I will explain this question. Okay. But here consider that sometimes we have limitations, some limitations on the number of poles because of speed. If the rated speed be high, we cannot increase the number of poles arbitrarily because we have limitations on supply frequency. Okay? In some applications, the motor RPM can be equal to, for example, 20 kilo RPM. So we cannot increase the number of poles because we have limitation on supply frequency. The best number for the number of poles is calculated considering objective function, your objective function. The slot pole combination is important decision in electrical machines, in design of electric motors, because the motor parameters, like as weight of active parts, is highly dependent on this combination. And in the next videos, I will explain you the effect of increasing or reducing the number of poles on machine weights, on machine dimensions. So, okay, I think this short explanation is good there, and I will explain the selection of number of poles in the next videos. The next decision is a decision about the number of stator slots. We have a variable named Q there that is equal to the number of stator slots divided by M times P. M is the number of phases, and Q is actually the number of stator slots per pole per phase. So when Q is an integer number, we have integral winding. The winding is called integral winding. And when Q is a float number, we have fractional winding. Fractional winding is used, for example, in brushless DC motors, BLDC motors, when the coil span is very low. For example, when the coil span is 1. So in this case, in this course, I will use a three-phase distributed winding. So, for example, here, if I select Q equal to 2, I can calculate the number of stator slots. The number of stator slots will be equal 2 times 3. The number of phases is equal 3 times the number of poles. For example, the number of poles here is 6. So the number of stator slots will be equal 36. Here in Excel file, we have a sheet named NSNM combination. Here, pole slot combination, for example, 6 pole and 8 slot. This is one combination. And we have some columns there that every column indicates one property of a motor. Actually, every record is one design. Okay, one design versus this sheet, main dimensions, analytic design of motor. So these numbers are calculated by running this analytic design. So you can select the best combination based on your objective. For example, sometimes your objective is the weight of motor. You want to design a motor based on objective function on the weight of the active part. You want to minimize the weight of active part. So you focus on this column. So for example, this is just example, and I will explain the calculation here in this sheet in the next videos. If I run this, okay, these numbers will be calculated automatically. I can add another record here. So I want to try design for 12 a motor with 12 poles, and if I consider Q equal 1, Q equal 1, 1 times 3 times 12 is 36 number of stator slots. So I fill here 36. So I want to add and compare the designed motor for this slot pole combination. If I press, okay, for example, let's compare this record and this record. So the weight of motor in this design is 10.2, but the weight of motor in this design is 12.7 kilograms. So the weight of active part of this design is lower than the weight of active parts in this design. But look at this number. The supply frequency here is higher than the supply frequency here in this design. And also the copper loss is different for these designs. So based on your objective function, you can select a proper combination for your application. Now let's talk about the calculation of line-to-line terminal voltage. This figure shows a three-phase bridge inverter, and this is load, a three-phase load. Yeah, our motor is there. So based on switching strategy that we are going to use for inverter, we can calculate the line-to-line terminal voltage. As you know, we have different switching strategies. For example, 6-step switching, sinusoidal PWM switching, or space vector modulation switching. So here is this equation is for 6-step switching. For example, if we use 6-step switching, the VAB, the line-to-line terminal voltage, is equal this expression. So the peak value of fundamental harmonic is equal 2 times SQRT of 3 times VD. That VD is the voltage of DC link divided by pi. So the RMS value is this. We can calculate the line-to-line terminal voltage considering the peak value of fundamental harmonic. Uh, I implemented the equations for these three strategies here in this Excel sheet. So if you consider this voltage as DC voltage battery pack, battery voltage of DC link, and if you consider 4 volt voltage drop over these elements, over these switches and diodes, so you can calculate the line-to-line terminal voltage. For example, for 6th step, I implemented this equation, and the VT in this equation is equal DC voltage minus voltage drop. As you can see here, the RMS value of output voltage is different for these strategies, and in this strategy the harmonic content is high, and in these strategies the harmonic content is lower. I selected this as space vector modulation, okay, in this example, in this design. So I set the value of line-to-line terminal voltage equal to 47 volts. And here we can select the motor connection, delta or star connection. Okay, let's conclude this video, this episode. So I explained the base speed, and we had a short explanation on the number of poles and the number of stator slots, and we will investigate the slot pole combination in details in the next videos. Okay, by adding another columns here in this Excel sheet and analyzing the numbers, considering multi-objective functions. And finally, we calculated the line-to-line terminal voltage for different switching strategies, and we selected the space vector modulation in our case, and I set the value of line-to-line terminal voltage equal to 47 volts. Okay, let's continue in the next videos.